It's your man Chiefs again. Good day. Today we are going to look at work, energy, and power. All right. I first of all make reference to our study guide, Revolutionary Science Workbook Study Guide 1, which was written by Norman Muvoti and Timothy Sibeko. Please make reference to it for the work that we are doing in these videos. That's the ISBN number that's up on the board. But what is work? Work is done on an object by a constant force F and is defined as F multiplied by change in x cos theta, where the F is the magnitude of the force and delta x is the magnitude of the displacement if the object is moving horizontally, or it can be delta y if the object is being moved upwards, and theta is the angle between the force and the displacement. So the important equation to keep in mind is the equation that says work done is equal to F multiplied by change in x multiplied by cos of theta. There are a few things to note. This is coming from our workbook. You must note that the force of a component of the force, or the force or a component of the force, must act parallel to the direction of the displacement. So in other words, we are saying if the object is moving, if the object is moving in this direction, the force must act parallel to the direction of the displacement, which is change in x, right? The force must be constant and must maintain contact with the object, like the force right here, okay? No work is done if the object does not move. So, no matter how much we apply a force, if the object does not move, even though I might get tired pushing or pulling, no work is being done. No work is done if the force is at a right angle to the motion. In other words, if I am carrying a bag and the angle between the force upwards and the direction of motion is 90 degrees, it means therefore no work is done. Because if you pull out your calculator and try to find cos of 90 degrees, you would find out that the cos of 90 is equal to 0. So therefore, no work is done if the force is at a right angle. Having said that, we must know that when we are calculating work done, we will come up with positive work done, right? Positive work done by an applied force on an object when theta is equal to 0 degrees. We have already explained what theta is. Theta is the angle between the direction and the applied force. Okay, if the angle is 0, like the applied force is parallel to the direction of the movements of the object, then we know that there is positive work done. Like in an instance where you got F applied. right? And then we can have negative work done in a situation where we have the angle theta being equal to 180 degrees. Like, for example, when we have friction, which is operating at 180 degrees to the change in x. Okay, so that's your frictional force in that direction. I should make that a little bit longer to show that the net force is here. So if I have my change in x here, from here to there, then the angle between the motion and the force applied is 180 degrees. In this instance, we are saying that there is negative work done. I've also explained that work done is equal to 0 or no work is done when theta is equal to 90 degrees. Like, for example, when something is lifted upwards and yet it's moving horizontally. All right. Let's move on to some questions. These are some of the questions that you would find in the study guide. Without further ado, an 800-gram metal moves to the right due to a force 10 newtons. The metal bar moves 10 centimeters on a frictionless surface. Okay? Mark and label two other forces which act on the metal bar. So now we got a metal bar. And this metal bar has got the force of 10 newtons in that direction. The other forces working on it will be the metal bar's weights as well as the normal force. Okay. So we are asked to indicate on here what other forces are working on it. All right, so that's the normal force upwards, and downwards will be the force of gravity, which is its weight. Next question, 1.2. Why do these forces do no work? Why do you think they do no work? Because they are working at 90 degrees to the change in displacement. In other words, what we see happening here is that according to our understanding where zero force or no work is done, all right, the theta in this case is equal to 90 degrees. Therefore, no work is done. Okay. So for simple 2 marks, you're stating that absolutely no work is being done in this instance because our theta is equal to 90 degrees. In other words, the angle between the change in x and the force is equal to 90 degrees. Calculate the amount of work done by the 10 Newton, 1.3. So 1.3, work done, we know work done is equal to F multiplied by change in x multiplied by cos theta. All right? Once again, these formulas you are finding at the back of every paper 1 question paper that you find yourself writing. So our work done, how much force do we have? We have a force of 10 newtons. What is the change in x? The change in x must be in meters. So here we are given it in centimeters. So 10 centimeters to meters, we divide by 100. So it's times 10 times 10 to the power negative 2. And the angle theta is cos 0 because it's parallel to the direction. If you do your calculations properly, you would find that our answer for the work done is joules. So as you have realized here in this answer, our work done is calculated in joules. The work done by the 10 Newton force is going to be 10 joules in this instance. All right, let's move on to the next question. It says then, calculate the amount of work done. Okay, we've done that, 1.3. Next question says, from the study guide also, for each of the following, calculate the work done. Each object moves 1.5 meters, and each object is resting on a frictionless surface. All right, so let's look at the first one. The first one is a 4 kg object, and this 4 kg object has an acceleration of 5 meters per second. But I know that in order to find work done, I use force. I am given mass and acceleration. I have often talked about how laws of physics interact with each other, come together. They never oppose each other. They rather work together for us to find out answers to questions. What law have we done can help us find a force when we are given acceleration and mass? Think about it. Mass and acceleration. Exactly. Newton's second law. So 2.1, I am going to find the force first by saying F is equal to mass times acceleration. In other words, 4 multiplied by 5, which gives me 20 newtons. That's my force. So the force along this way is 20 newtons, right? Now, for me to come up with the answer of the work done in this instance, W is equal to F multiplied by changing X in meters times cos of the angle between F and changing X. All right, so my force is 20 multiplied by changing X, 1.5 meters, multiplied by cos 0, because they are parallel. All right, so 20 multiplied by 1.5, pull out your calculator, very simple question, times cos 0 degrees, that should give you 30 joules. Okay, so that question is done. Question 2.2. Let's move on. Let's hope this marker writes better. All right, 2.2 says, now it's at 45 degrees. You must remember resolution of forces. Okay? I'll quickly revise that with you. If I am to resolve this force of 20 newtons, bringing it to the horizontal, right? We might not have covered it at any point in our presentations, but you would agree with me there is an fx component here and an fy component there, fx over fy according to trigonometry is equal to cos of 45, right? No, f, which is f here, that is adjacent over hypotenuse. So fx over x is equal to cos of 45, adjacent over hypotenuse. So your fx is given by f cos of 45. All right, this is just to remind you on areas on how to resolve forces if you have forgotten that very aspect. But guess what? Our formula already for calculating work done helps us to calculate work done even at an angle. In other words, when we are calculating work done and given a force, we multiply the force by the change in x times the cos of the angle between change in x and the force. The change in x here is in that direction. The angle between change in x and the force is 45. So we are going to say simply 20 times 1,5 cos of 45. You can pull out your faithful calculator. My blue baby is next to me here. I will do exactly the same thing. Calculate with me. 20 multiplied by 1,5 multiplied by cos of 45 degrees is equal to 21,21. And always remember to put in your units in joules. Mind you, these questions are coming from our workbook, all right? So it helps you practice, our study guide helps you practice some of these questions and some of these areas. 2.4 is an object of 4 kg that's been lifted upwards. Okay, the question is not clear if the object is moving 1.5 meters, all right, horizontally or vertically. So if it is moving vertically, let's have those two. Well, let's start with if moving horizontally. If moving horizontally, right, we know that that force will do no work because it's at 90 degrees. Okay? If it's moving horizontally, no work is done. By the force of 20 newtons. Okay, my markers are beginning to give up now quite quickly. All right, but if it is moving vertically, which is upwards, if it's moving upwards 1.5 meters, but if moving upwards, the work done will be equal to F multiplied by change in x times cos of theta. Your F there is 25 newtons multiplied by 1,5 multiplied by cos of 0, because it will be parallel which is at 0 degrees. All right, so pull out your calculator once again and quickly multiply with me. 25 times 1,5 times cos of 0, which gives you 37,5 joules. Okay, so this question number 2 is done. Let's move on to question number 3, which says a man pulls a sled across the ice surface with a force of 72 newtons at 60 degrees to the horizontal. How much work is done by the man on the sled through 10 meters? Okay, so let's try that one again. Leave these formulas on because the very same formula should be applicable. So now what is different? Only difference is force of 72, question 3.1. The sled maintains, how much work is done by the man on the sled through 10 meters times 10 times cos of angle 60 degrees. Once again, we need to calculate that. Bring the blue baby closer and let's calculate together. 72 times 10 multiplied by cos of 60 degrees is equal to 360 joules. Okay. 3.2 says the sled maintains a constant velocity. We have met this a number of times. Do you remember my emphasis each time we talk about a constant velocity? Right? What frictional force acts on the sled? Each time we talk about a constant velocity, we refer to a constant velocity as a situation where acceleration is equal to 0. In other words, the object is not accelerating. 0 meters per second squared. The object is not accelerating. In other words, if there is friction on the object and the object is not accelerating, what do we know? Let's just put a free body diagram here. If object is not accelerating, let's use a different color. If object is not accelerating, and a force is applied, right? It means that in this instance, your frictional force is equal to applied force. Now the question is asking, what frictional force acts on the sled? In other words, in this instance, the frictional force, small f, is going to be equal to the force that the sled is. All right, there it is at an angle of 60 degrees, 70. If we are going to resolve it on the horizontal, it will be 70. Remember our resolution? cos of 60 degrees. That will be our force. Our calculator out, I think the answer is 35.70. Cos of 60 is equal to 35, and that force is in newtons. Okay, so it's equal to the force along the horizontal. Okay, these two forces are equal. Next question says, a horizontal force of 8 newtons is applied to a 2 kg mass. The mass moves a distance of 5 meters to the right against the frictional force of 4 newtons. Calculate the work done by 8 newton force. All right? That's question 6. Very easy. Work done is equal to F, change in x, multiplied by cos of theta. That's 8 times 5 meters times cos of the angle, which is cos of 0 degrees again. So 8 times 5 will be 40. Our answer there is 40 joules. Okay. That does it. Another question that we can look at before we come to the end. Sorry, the top parts you cannot see, so let me read it off the screen here. It is a system all right. In the diagram below, a 4 kg block, all right, is lying on a rough surface, horizontal surface, which is connected to a 6 kg block by a right inextensible string passing over a light frictionless pulley. All right? Good. Now, when the blocks are released, the 6 kg falls through a vertical distance of 1,6. As you can see in the diagram here, right? Draw and label a free body diagram for the 6 kg block. Once again, the things that we did in the previous videos are coming back to haunt us. Or the same questions are being asked. We're looking for the free body diagram here of the 6 kg block. So we will have the weights working downwards and the tension. Very simple for 2 marks. 5.3 then says, calculate the work done by the gravitational force on the 6 kg block. So now, work done by gravitational force is work done by the weight of the object. So the work done by W is equal to, once again, F, or force, times change in x, times cos of 0 degrees, because it's along the plane. Okay, that's the direction. So W, in this instance, which is the force here, let's put here, work done therefore by W, weights times change in x, cos of 0 degrees. The weight of the objects we are not given. How do we calculate the weight? The weight is found by multiplying the mass times acceleration due to gravity, which is 9,8 meters per second squared, times change in x, which we are given here as 1,6 multiplied by cos of 0 degrees. Once again, I encourage you to take out your calculator and work it out together with me. That's 6 multiplied by 9,8 multiplied by the distance 1,6 multiplied by the cos of the angle 0, which is equal to 94,08. Joules. Okay, and there is my answer for 5.3. So, what is it that we have discovered right now? Well, we have been able to use aspects of Newton's second law. We have been able to use aspects of weight. We have been able to use aspects of work to find the work done by an object, and formula force is equal to mass times acceleration in our calculations of work done. What can we expect then in the next lesson? In the next lesson, I wish to look at work energy theorem with you. What the work energy theorem states is that the work done on an object by a net force is equal to change in its kinetic energy. Which means that in the next lesson, we are going to look at what kinetic energy is. We have already done questions that look at kinetic energy, so we will revise the calculation of kinetic energy. I will explain why work done on an object by a net force is equal to its change in kinetic energy. Think of it this way: if an object is going to change its initial velocity to a particular velocity, right? It means that there has been a net force that has occurred. So from that end, work has been done. If an object has an initial velocity and now has a particular final velocity, using our formula of kinetic energy, we can be able to relate kinetic energy to the work energy theorem. In other words, the net work done on an object causes a change in the object's kinetic energy, be it horizontally, be it vertically, or on an inclined plane. At the end of this lesson, I want you to start thinking about how we calculate EK as being equal to half mv squared. And in that light, start imagining the change in kinetic energy to be worked out as work done is equal to a change in EK, and what you think it entails. Well, that's it for this moment. From Chibs, it's ciao.